Okay. Yeah. Okay, get started. So. Yeah. Really good feedback. How's the volume go? Okay, so I'm just going to hide you.
I saw that. I've got several files of those.
We're going analog.
Are they going to digitize all the sky news? Well, they've done that with National Geographic. So as long as you're a member, you can first have access to all the latest facts That's right. The only thing is that we could then...
Are we better? Can you guys hear me? Is it coming through? Okay, great. Okay. Thank you, Chris. Okay, so I have, for reasons unknown, decided to talk about astronomical measurement units this month. Much like the air outside, it's a really dry topic. I will try to, lighten things up along the way as best I can, with, jokes. But I really want to talk about astronomical measurement units because I think they're really important, and I think it's really important to understand units and how they play into astronomy and how we use them and why the standardization of them is important. And I just use the word standardization, which, you guys know is riveting. But it is really important, and I'll try to give as many practical examples as I can, in terms of how it plays into astronomy and the kind of things that you come across. And I think it's another important thing to keep in mind here is that, if you're going to open up, sky charts, textbooks, reading stuff on the internet, and you're going to come across some of these units, and they might seem a little bit obscure. You might not necessarily know what they are. So hopefully, I can provide a little bit of education in that matter. So let's get to the dryness. What is a unit? A unit of measurement is a definite magnitude of physical quantity defined and adopted by convention and/or by law that is used as a standard for measurement of the same physical quantity. Basically meaning, let's have a common language for how we're describing physical properties, right? We want to, if I'm talking to somebody and I say to them, I have, my car gets 8 furlongs to the hog's head, they have no idea what I'm talking about, right? If you tell them, if you know what I'm talking about, then wow. But chances are you don't. So you're going to want to have some standardization so that you can speak in a common language. And not only that, it's really important that these units are not just standard amongst our conversation, but in the scientific literature and everything that we're doing there, because you want to make sure that what I interpret as a kilogram is not what, say, the United States interprets as a kilogram. It's not that they use kilograms, of course. Because if you have a difference there, then scientific results and scientific data can be potentially wrong. Right? So we've actually only really got 7 units to work with. With these 7 units that you see here, you can pretty well describe the universe. Right? Everything that we know, with the exception, without, mathematical equations and all that. But in terms of physical properties, this is everything. Right? So running down the list, we have meters. Everyone's pretty familiar with that. Kilograms, measure of mass, seconds, time. Electric current might not run into as much, but described in amperes. Temperature, this is Kelvin. It's going to be for use in Celsius. And moles, which you probably remember being confused by in high school chemistry. And that's an amount of a substance, so one of the base ones that we use. And also candelas, which are luminous intensity. We'll talk about some of these. I'm going to focus on more of the ones that pertain to astronomy. Like, honestly, that we don't really run into electrical current all that much unless you're dealing with amounts. So, one of the really kind of cool things too about the way that the SI, and when I say that these are SI base units, like there's this is internationally recognized. Like this is what scientists everywhere use, right? So there's a lot of work and effort that went into figuring all this stuff out. There's a lot of words up here, and the reason why there's a lot of words up here is mostly just to show you just how precisely defined a lot of these things are. And one of the really important aspects of it is that the understanding, the definition of these units, they are almost, with the exception, I think, of the kilogram, they are all determined based on physical properties, right? So physical constants in the universe, right? So for instance, the speed of light is a constant in the universe, and we know that, so we can then use that to define these units that allow us to describe everything else. So you get some real solid consistency. That's also why we end up with these really wacky numbers, because the really wacky numbers come from the fact that we defined these units before we found matching physical properties to describe them with. So we didn't want to change roughly what a second was, but we wanted to keep calling it a second. We wanted that second to be, 1, 2, 3, 4, right? Fast, whatever. But we didn't want to have to dramatically change that, but we wanted a physical property that we could describe it with, so then we ended up with this ridiculous definition. Right? But it's accurate, and it works. The other kind of funny thing is that you end up finding yourself describing units in terms of other units. So you get these correlations. You notice that the kilogram is actually out by itself. So like I was saying, it's one of the ones that we just kind of have arbitrarily defined. It's kind of just a chunk of, I forget what it's made of, but it's basically a chunk of material that is in France somewhere, and they just make sure that this is what a kilogram is. And there are actually comparison kilograms around the world. Now, of course, when we're talking about units, we need to have prefixes. So if you really wanted to be able to describe, a septillion grams, you would need to use the word yotta, which is, I don't know, I think it sounds cool. Like a yottagram would be 1 septillion grams. Right? Kind of nice. You're probably very familiar with these. As computing has accelerated, you start running into this, the mega to giga comparison. So if you ever wonder where any of that comes from, that's what this is. That's where it's from. You will, sometimes you'll run across this in astronomy when you're talking about ridiculous distances and stuff like that. Like things like, a megaparsec, which sounds really cool and sci-fi, which really just means a million parsecs. All right? So if you ever hear the term mega, yeah, it just means a million. Yeah, and then going the other way, so these are more prefixes, but this is going on the other side, they're getting smaller. So, when you hear the word micro, similarly, that's a millionth of something. These are probably less used in, really these are less used in astronomy, but so let's talk about standardization, and it is a really important aspect of these units, because you want to be able to, again, you want to be able to speak in this common language, right? And you'll notice there's one key outlier, well, there's a handful of key outliers. There's a really big one over there of countries that have not fully adopted the metric system, or partially adopted the metric system. Thankfully, most of the science that's, well, I should say most, a lot of the science that's done in the United States is, they do tend to use the metric system, but you will run into situations where, people are talking in files and so on and so forth, generally outside of academic circles, but in the amateur astronomy field, sometimes maybe you might run across that. So you have to get into the habit of converting things. And I talked about this a little bit, but why do we need units? Well, we need them to describe things, right? We want to, I want to know how much weight I've gained over the Christmas holidays. Actually, I don't, but I can, because we have a measure of mass, right? So I can tell this is how much weight I put on eating all that delicious food. And it's not just about why we need these units. Have a seat. So it's not just about why we need the units, it's why we need to understand these units. And this is kind of a classic failure that happened with the Mars Climate Orbiter, where they had one group working in metric, and they had one group working in imperial. And there was a piece of software, or a part of the software, where it was expecting the units in Newton seconds, which is a common unit used in space flight and engineering, right? But instead, they got it in pound seconds, which is also a common unit used in engineering. The problem was that they didn't know which language that they were speaking to each other, right? So you give them the number in pound seconds, and they thought you were talking about Newton seconds, and what ends up happening is this was supposed to be your trajectory. That's your actual trajectory. And you come in a little bit too close to the planet, and kaboom, you lose a multi-million-dollar spacecraft, all because of a little mishap with units. So, yeah. So we'll jump into some examples here. This is temperature. Kelvin is a really easy one. You'll see Kelvin used to describe temperatures a lot in especially just in general when you're talking about like academic stuff. I think you almost always see Kelvin to describe like the temperature of the sun. And I mean, I think we should use it to describe Winnipeg in December, because 258 sounds way better than -20. That's me. And yeah, the conversion is really simple. It's not like Fahrenheit, where you have to do some multiply by this and add a certain number that I don't remember off the top of my head. It is basically just a shift where the lowest temperature is 0, and then everything above that is just the same as Celsius, right? It works at the same scale. So you just have to subtract. You just have to take like Celsius is equal to Kelvin minus 273.50. It's a pretty easy conversion to make. So, and really, when you're talking about something like the sun's photosphere, which is 5,000–6,000 degrees Celsius, you can call that Celsius. Like you're pretty close, right? So if you ever hear Kelvin, Celsius, you can pretty well line them up when you're talking about temperatures that are that hot. It's close enough. Getting into time, sometimes you'll run across Julian time, and a Julian year, for instance, is 365.25 days, and that's not to be confused with the Gregorian year, which is 365.25 days. That's not to be confused with the Salian year, which is 365.25 165, 184, 190, 87, 81 days. Probably won't ever matter to you all that much, but just to know that when people are talking about a Julian year, they are talking about that one. You will see this come up sometimes in astronomical catalogs, so just so you're aware of that. Julian dates, similar. This is just a way of just having a nice standard number, nice standard single number for time without having to worry about basically, having to worry about things like days, and years and whatever. It's just you have one day, right, or one number of days and some percentage of a day, right? So for instance, right now it's fixed. Almost dead on, right? And this is also kind of nice. You'll notice in catalogs and whatnot where you'll actually come across this, these Julian epochs. So they'll say that, oh, this star catalog is good for 2000, right? And this is really important because and we talked about this in other beginner sessions, but the Earth undergoes what we call precession, where it kind of wobbles on its axis over time. And what that means is that the position of the stars in the sky tend to change over time. And this change isn't really noticeable over a couple of years. But when you start talking about, say, 20 years, maybe 20 years, but definitely on a 50-year scale, you actually start to notice that things are a little bit off. And so in order to correct for that, you can do this, or you can just wait for the new star catalog to come out, which will probably be configured for 2050. We'll get into angles. Hopefully, but we're not going to get into any kind of like trigonometry or anything like that, so don't be scared. But I know sometimes people see degrees and the word arc, and they might get a little scared. But we'll try to make this fairly simple. The way to think about degrees, and just to give you a little bit of heads up, this is going to basically be used to describe distances of things in the sky. And we'll get into more of those examples in a bit. So when we're talking about a degree is just 1/360th of a circle, right? So this tiny little red sliver is 1 degree, right? Everybody knows this is 90, it's 180, etc. Now, sometimes a degree is not enough precision for us, so we break that down into an arc minute, which is frustratingly 1/60th of a degree, and then we have an arc second, which is 1/60th of an arc minute. You will predominantly be seeing these two if you are referencing astronomical things. So remembering these, just some examples. We have some visual ones for you as well. But for instance, the angular diameter of the Andromeda galaxy is about 4 degrees, roughly. So if you were to look up in the sky, that is about as much. That is about the size that it takes up end to end. The angular diameter of the moon varies between 29 and 34 arc minutes. So 34 would be like a supermoon, and then 29 is when it is a little bit further away from us. The angular resolution of your eye is about 1 to 2 arc minutes. So that's, can I tell apart a couple of points is basically what that is, and that'll obviously vary from person to person, but that's roughly what it is. The angular diameter of Pluto, and again, this is from Earth, looking out into the night sky, is about 0.1 of an arc second. The angular resolution of Hubble is 0.05 arc seconds. So that's about as good as Hubble is. To give you a little bit more visualization of this, I wrote this on Wikipedia, as I do most things, but it's a fantastic chart because everything that you see on here is actually the relative size that it's supposed to be. I like the comparison too of the moon and the sun are actually both on here, right? So the sun lines are these red lines, and then the black lines are the moon lines, right? And this is roughly how much the moon will shift by, right? In terms of its angular size, and then this is how much the sun will shift by its angular size. Also, all the planets are on here as well. So you can actually see that Venus, being as close as it is to us, takes up a significant portion of the significant angular diameter in the sky. And then going down, Jupiter, just because of how massive it is, Mars and Saturn are actually kind of close. Again, a lot of this fluctuates based on how far away they are from us. But you can see relative sizes of how big these are, especially compared to something like the moon in the night sky. So if you just imagine what the moon would look like right now, and then picture Venus, right? That's how big Venus would be in the night sky. There's some handy tricks that you can use to determine how far apart things are, just using your hand. Basically, you take your hand, extend it out, well, you hold, assuming it's attached to your arm, and extend it away from your body. And if you hold up a pinky finger, that's about 1 hand. And whoa, dude, is about 25. And if you're looking for, you will be looking at stars, and you may want some kind of reference. And this will come in handy a lot too. Getting to know these, getting comfortable with these angular diameters will come in handy when you're trying to find things, and you're trying to use star charts to locate, dimmer objects and harder to find things, because you're going to find that the best way to get there might, yes, star hopping helps, but in order to zero in on it, you may want to use a little bit of like, oh, okay, I know that this is so many degrees from this that I can just kind of shift my telescope down a little bit, knowing how many degrees that is after looking at the star chart. It helps keep your frame of reference correct. So, the Big Dipper is kind of a good one to keep in mind if you're looking for references to use in the night sky. So this is about 10 degrees. That's about 5 degrees. This point to this point is about 15, and I think this is about 20 to 25 or something like that. And like I was saying, with the holding your fist out, if you're ever really tempted, especially if you're having like a really bad night and you just can't find anything, you can punch the Big Dipper right in the dipper, and you will know that those two stars will be accurately 10 degrees apart. Continuing to talk about length. Continuing to talk about length, angstroms. You will come across these in the discussion of things like, typically things like, radio astronomy, X-ray astronomy, basically all the parts of the electromagnetic spectrum that we can't see with our eyeballs. You will occasionally see these also in the sense used in cases of filters. Angstroms will come up. I don't know how commonly angstroms are really used. I feel like nanometers is kind of a more accepted one. Angstroms is kind of falling out. I don't know. It depends on, again, this comes down to the standard language and whatnot, where people still hold on to old ones. Personally, I've always been a fan of the beard second, which is approximately the length that an average beard grows in 1 second, which, for reference, is about 50 to 100 angstroms, which, you're just waiting for a second. Yeah, my beard just grew, another 50 to 100 angstroms or 10 nanometers. I'm joking, but that is actually kind of cool to think about. I will not have that again. My beard is not that is me, by the way. If that wasn't clear, that's how I used to look. You'll also come across the astronomical unit, which is just a measure of distance, and it's a pretty standard one. It's the distance from the sun to the Earth, right? But it's a really good unit of distance to have for trying to describe. Distances within our own solar system. You can quickly tell that, once you get outside of the solar system, astronomical units become kind of pointless. No one's going to describe, this in terms of, you're not going to say 266,000 astronomical units is approximately 7 or 8, But for the sun to Pluto, this is a nice number that we can use, right? You may be wondering, well, this one wouldn't get to the center of the universe. I mean, we all know where the center of the universe is. Yeah, exactly, right? It's about as far as it is from here to Toronto. Yeah. So, I guess that shows. So, parsecs. Parsecs are also used. This is also a classic Star Wars reference, and now that Star Wars is back in favor with everyone, you can kind of start talking about this stuff. Not everyone like growing multiple schools. But the whole Kessel Run thing, you know, where he does it in so many parsecs, it was used wrong, so very, very wrong. A parsec is a measure of distance, not a measure of time. And it is based on, and it sounds cool, right? Like it's one of those sci-fi kind of sounding numbers, or units, which I think is why they use it in Star Wars. Because it sounds better than a meter, I guess, I don't know. Or light year. But the way that, so what a parsec is, technically though, is if you imagine, so if you come in and you say, okay, I'm Earth, right? And I'm orbiting the sun, right? You've got the sun, the Earth out here, and the Earth out there, right? And this is as far as the Earth goes. And what you can do is you can actually use this to determine the distance to objects. And this has been fantastic. This has really helped us to calibrate how far away things actually are. This is really, really important for measuring astronomical distances. It doesn't allow you to measure things that are very, very far away from you, but allows you to use other things to calibrate against them. So we'll talk about that in another box, I'm sure. But the way that a parsec is defined is if I'm imagining a star out here at 1 arc second, this is the angle that determines a parsec, right? And 1 arc second is, it's kind of arbitrary, but what it allows us to do is say that this is the distance of a parsec. Okay? So again, parsecs, they are useful in some areas, in others. The Sun to the Proxima Centauri, this makes a lot more sense than astronomical units all of a sudden. 1.29 parsecs, kind of nice. But again, things like Milky Way to the Andromeda Galaxy, 766,000, not that useful. And again, for small things, not that useful. Then we get into light years, so now we've moved on a little bit further in terms of distance. And a light year is, I think, hopefully we should know this, but a light year is how long, sorry, I just tripped myself up there. A light year is the distance it takes for light to travel in 1 year. So that's pretty far. But you have to remember too that light is also moving very, very fast, right? So it's a lot of kilometers, right? Also a lot of astronomical units. I mean, technically it's also, well, it's not a lot of parsecs. And again, it's close to parsecs, so you will typically not actually see things measured in parsecs, but you will more commonly see them measured in years. So,
what does the IAU prefer if they're describing the distance? Do they use parsecs or light years?
You know, I'm not sure. I feel like I see I feel like I only ever see parsecs in like academic papers, you know, like back when I was in school. But I feel like light years is probably the more commonly accepted one. I think they're both commonly used though. I mean, I don't know if there's a preference. I could look it up. I mean, I'd have to look it up. But yeah, good question. I remember one time there was also another question I had once upon a time that was about why radians were not used, which would have made a lot more sense for measuring angular distances. And as far as I could tell, there was no good reason. It was kind of like what we ended up with. So sometimes those decisions are somewhat arbitrary. And I feel like the difference between a light year and a parsec might be something. in terms of light years, just to give you an idea of, you know, how far things away from would be. I don't know how well you can read this, but this is the sun, so we are here, right? This is the Milky Way galaxy. This is the galaxy that we are in. So there are not other, there are other galaxies out there, but this is ours. And these numbers here are the distances from the sun in light years. So if we head out this far, this is about 15,000 light years, right? So if you think about it, like our radio signals, like haven't, you know, since we started broadcasting radio signals 100 years ago or whatever, they haven't gone past here. You know, it takes a long time to travel this distance. Even. You know, this basically means that if you were traveling at the speed of light, which you can't do, it would take you 15,000 years to get out here. And it extends out to 30,000 light years at that point, and then from here to just past the center of the galaxy, you know, it's 45,000 light years and 60,000 light years and then 75,000 light years to get to the other side of the galaxy. So it's quite a long ways. Anyway, I've eaten up all my time and distance, so I'll call it there. Thanks.
Anniversary of Hillblock, or West, rather, Common West. Who remembers it? We all have gray hair. That's regarded as one of the 10 best comets of the modern era. It was a beautiful comet. You could see the tail rising. About an hour before the comet hit. You never had to wonder where it was because all of this stuff that's picking up in my old black and white photograph here. Well, you saw this stuff as it came over the horizon. And that March had a lot of clear skies in it too. So. But you can see I had the camera set up on my Celestron, which was polar aligned and tilted over to one side, and I didn't have a camera mount that would allow me to turn it so the horizon was parallel. Anyway, is that on?
That looks like a red light beeps occasionally. Anyway, welcome to December. Welcome to winter. Doesn't look like it's going to warm up anywhere in the near term, so we're into this kind of observing now. That was a pretty cold morning, as I recall. But we got a very nice November out of it, with actually a fair number of pretty nice skies out there. So how many of you are here for the first time? We have a couple. Well, welcome to the Winnipeg Center's monthly meeting. As you can see here from our schedule, we'll start off with the beginner session, which Brendan has already done for you. And I'll do a couple of announcements. Then we have Brian coming down to do What's Up. And What's Up is essentially what's coming in the next month in the sky that you might want to go and watch. And Ian Cameron's going to do What's New, which is new events in astronomy, new discoveries, new research. And then after we break for coffee and cookies, and we have some books to give away somewhere, Ian's bringing them in. We will have Dr. Danielle Bahoud talking to us about her research on solar events. Tonight, I've made arrangements for us to have pizza at the Hub. I know when we did this last year, I got a fair number of favorable comments about it. And of course, it means you can walk over there instead of driving to Boston Pizza. So we'll try it out again this year. And if it works out and you sort of elect to go with it, then we'll continue to have pizza at the Hub as long as they can make space for us. Sometimes we will run into university affairs that are going on, and they have some kind of party reserve. We might not be able to do that.
Are minors allowed in there, Jerry?
Big
Minors, are they allowed in there?
Minors are not allowed in. That is the biggest problem with the Hub. Well, they weren't last year. Now, I don't know if they managed to get a change in their licensing to allow that. It's something I didn't check
We'll leave them
on.
outside in the snow.
Yeah, I guess it won't be all right. I got a note in the email a few days back that Steve Malia, who is owner of Ontario Telescopes, has purchased 30 copies of the Explore the Universe guide and is going to send one out to every center. And it sounds like he'll keep one for himself because we have 29 centers. But the Explore the Universe program is one of those observing programs that the RASC has where you can get a certificate and a badge if you complete all of the observations. Has anybody here done that? We had one member that had. I noticed that we're falling a little bit behind in some of the observing certificates. Maybe it has something to do with -30 temperature. But anyway, this is kind of a beginner's observing certificate. So you observe fairly easy to find objects for the most part. The guide is the book you see here, which I couldn't find a very high resolution image of. But it actually explains how to do each one of the items that are necessary to get your certificate and your badge or your little pin they give you. Many of the observing certificates that you can get through the RASC come with pins. I can see the day when we'll have some of you here with the sash across your chest and all these pins on it, the way that Boy Scouts do. Although that might be going too far. I'm going to show you a few other little certificates that are put up by other organizations. Anyway, Steve has said that this has to go to an under 18 RASC member. And I see that there's only about 20 or 30 of you that will qualify here. But I expect to have it in time for the January meeting, so if you have youngsters in mind who think they might like to get the copy that Steve is providing, then have them show up at the January meeting. The badge that's given out for that is showing up here. And the terminology, or in terms of 3 things to give away, the national organization has decided that they will have a program whereby centers can obtain as many as 100 copies of Sky News each time it's published, which is 6 times a year, at a cost of $0.25 each. Now, we all get Sky News as a part of our regular membership with the RASC, so these copies of Sky News are to give out at star parties and any public event that we give or that you as individuals give. So if you want to be able to pass out a copy of Sky News, I'm having them shipped to me right away, but I'll bring them into the meetings. But you can ask me for copies. We discussed this a little bit online between some members of the council and thought that it would be a good idea to provide a fairly large number of them to the planetarium so that they could hand them out. And we would bring them in here for people who are not members, and you could go home with them, although we got a pretty generous supply of giveaway magazines down here today. And in any event, it becomes another resource to hand out to the public to promote astronomy. The total cost of the center is only $150 a year, so we don't think that it will be a particularly onerous problem for us to afford at all. And so I'm also showing you a picture of the current web page for Sky News. The RASC has been building that up quite a bit. They are anxious that you use it, and it's certainly a good resource to sort of keep track of what's going on in the sky, saying that Sky and Telescope or Astronomy magazine web pages. But of course, the RASC will probably be able to offer you a few little deals on some of these supporters and advertisers on the site, because it is directed toward the centers and toward the North National Organization. Terry sent this note out a week and a half ago, something like that, about another website that he's come across that has online observing guides similar to the observing guides that the RASC has for its various badges and certificates. This one, pretty interesting and pretty comprehensive site, is called faintfuzzies.com, and they have 21 guides in there, and I didn't list them all, but some of the titles on those guides are given here. Well, you might be familiar with the Herschel 400. For those of you who are new, Herschel was an observer in the 17th century, 1700s in England, and he compiled a list of quite a few objects in the sky. He made a catalog of them, and the Herschel 400 are the sort of brightest and are most prominent of the 400 most prominent objects out of that catalog. So you can get certificates from the RASC for observing a certain number of these, and in particular the American Astronomical Society also hands out awards for people who observe those 400 objects and others. Now we typically will sort of mark the Messier's objects from Messier's catalog of 110 objects as being the beginner's deep sky observing certificate. This is one that you can go on to once you've got a lot more practice at it. However, when you get into this, the local group of galaxies, well, there are 3 bright galaxies in the local group: the Milky Way, the Andromeda Galaxy, and the M33. But there's a lot more small dwarf galaxies that probably would have to take you to the southern hemisphere if you wanted to make any kind of a hit on that catalog. And then you get the Vorontsov, the Yaminov catalog of interacting galaxies. There are 2 versions of that, or 2, volume 1 and volume 2. If you're going to go for this one, you're looking at rather substantial telescopes to be able to. But on the other hand, at that level of brightness, everything looks the same, so you can get through them pretty quickly because you're probably not going to spend, well, no, these are interacting galaxies. There'll be some nearby ones that are pretty interesting. Probably things like M51, which is a nice spiral galaxy. And then the Herschel objects comes in 3 volumes here, and then we have Palomar catalog, and so on and so forth through a total of 21 different observing lists. Some of you can order them in hard copy or spiral bound, but they're all completely freely available as PDF files on the online. So even if you don't want to go for the certificates that might be offered, you could at least use them to find some really challenging objects, say at the Sprucewood Star Party. Sylvia, is she here today? Yes, there you are. Maybe we should have a Viliamina Vorontsov observing challenge. Here's one of the, wrong button here. Here's one of the catalog, or one of the pages, page 55 in the Viliamina Vorontsov Viliamina catalog here. And so this is number 806. This is what it looks like, presumably in the Palomar survey or one of similar surveys of galaxies by professionals. And you can use this as a way of finding it. Here in Pegasus and zero in on this group of stars, and then you have to go to the photographs to be able to really identify it. Magnitude 14.38, that's not too bad. You should be able to find that with about a 10-inch Thomsonian. There's a challenge for you, Stanley. None of this Messier stuff. This is actually a good one for Ray. Ray, there is a catalog of planetary nebula there. Ray likes that. So Ray, break out the 25. Let's get going on this speed stuff. Okay, Danielle, here. Will be okay. The university is continuing with its open house on the telescope on the university college, a little bit to the east of us from here. But that will be suspended, I expect, for December, since the university is closed in the last Wednesday of this month.
It is closed. It will be closed. There's no...
The planetarium and anyway, we'll watch for that at the end of January. But a reminder to let you know that if you want to have a look at their telescope and get some kind of a slideshow in the planetarium, it's certainly available to you and to anybody in the public who wants to come along. Nice little planetarium. I've had many a very good sleep in there. That's on you, Ian. Archives. I have 4 or 5 filing cabinets full of the Winnipeg Center archives, all on glorious pieces of paper. And they're mostly pretty boring. There's a couple of interesting things. So they go back to 1911 when we started this center. And I think they should be digitized. So I kind of like to collect a few people who have scanners who will take home various bits and pieces of it over the years and scan it, and maybe we'll throw it all together into a PDF and pass part of it to the National Archives and put it in our own website. Probably the most interesting thing in it is the fellow back in about 1917 or 20 who became a member. In those days you had to be invited to be a member because it was all sort of snooty people from the university and the business community, and there were only about 12 of them. Anyway, he got himself invited in, and it turned out once he was in that he believed the earth was flat. And so the letters going back and forth, one members of the RASC Center at that time saying, "You should never have let this guy in. Did you cash his check?" "No, I haven't cashed his check yet." "Well, send it back to him." Because he's really just saying that he believes the earth is flat, and look, he's got enough credibility that the RASC gave him a membership. Anyway. We actually did throw somebody out of the club once back. So the rest of it's pretty boring stuff. List of an enormous number of lists of complaints about people who didn't get their handbook. We still get a few of those, but they're not very common anymore. But anyway, if you've got a scanner and you want to sort of help out, and even better, if you want to be the person who organizes this thing, then I'd certainly be happy to pass this material along. I figure you got about, well, let's say, I hope you get 15 more years to do it, because after that I'll probably be dead. Who knows where those things will end up. It's been a bit of a challenge to keep a lot of them, and we're missing a large number of years from about the 1950s to the 1970s. If any of you have them in your house, I'd like to get them back. National awards, they're still soliciting nominations for national awards. I mentioned this last time, and the deadline for that is running pretty close now. I noticed the new issue of the journal that came today is still advertising for nomination. So you'll have that. You can get a hard copy of it. You'll have that in the mail, otherwise it's online for you. But I would like to, at least if you think some of these people are eligible for these awards, that you should at least let me know, and we'll help put together some kind of a nomination. They went through these before. A Champ Medal is essentially for fairly substantial research project going over a long period of time, and there are not very many amateur astronomers who do that. It's not an award for professionals. Ken Chilton Prize is more for single item research-like projects where you might participate in a larger project to observe stars or asteroids or things like that. And there's some interesting NASA projects going on right now to monitor Jupiter, for instance, while a spacecraft is in orbit around it, that sort of thing. President's Award is given out by the President to anybody who he thinks deserves it. And so there's no nomination for that. The ELAC Award is an award for public outreach. Simon Newcomb Award is for writing, and there are various service awards, and that's the one I'd really like you to send to me, anybody you think who's done a substantial amount of work, not only in this center, but perhaps even nationally, so that we can get them a national service award. Of course, we have our own local service award, but the national one entitle you to much more. You get, well, I don't know, maybe get coffee. They won't even pay your way down to Toronto, but they will give you entry into the General Assembly meetings. And so these are sent to Randy Atwood, but if you think of people that could be nominated for these but don't have the time to write up the nomination, let me know, and then I'll do something to push it on the national. Once again, mention that Randy is our executive director, is talking about a national star party on July the 29th. And if it comes to pass, we'll certainly participate locally. We have, of course, shortly after that, less than a month after that, the rather large partial eclipse of the sun that we'll be working on as well. Telescope loans, Stan tells me there are no persons wanting telescopes right now, so those of you that have them can keep them, but if you do want a telescope, you can talk to Stan, and he'll put you on the list, and then when the telescope comes next month, they will be loaned out again to people who want to take them home. There's no charge for that. You can keep them for a month at least, and you probably would find it useful to take that out to the members observing night, which we have, well, in this case, tomorrow night. Brian, is that going to go on?
I don't think so.
You don't think so?
Attaboy, Brian.
Minus 30, challenging you too much?
Come on, Brian.
You sort of have a limit when Canon cameras fail. Is it about minus 25? So, I can't. Probably not tomorrow night. We'll have another night. See, the summers are the nights are too short to have a members observing night, and the winters are too cold. So we only squeeze in about 5 months out of the year. But anyway, typically we would have a members observing night on the Saturday following the meeting. And if you borrow one of the telescopes and take it to that, you'll find people who can show you how to use it. Or if you own your own telescope and don't know how to use it. Winicentrics, I've got Megan's email here, but we'll have a new editor by next month, and I'll send a message out about that. We always like photos for Winicentrics, our little newsletter. You all got an email if you're a member of the center, and we have your email on file, but you all got an email with your copy of the journal for this month, or of the Winicentrics. And this brief little thing, if you aren't on the email discussion list, then this is how you get onto it. So you just really have to remember that email address. But you can email me, and I'll pass it on to you. So that comes to the end of our meetings, and we'll go back to our. Anybody else have anything they want to add? Stan, are there any calendars? No.
I have 3 calendars left, $10 a piece.
How many?
3.
3 left. Well, we're not discounting them yet. It's $1 a month for a calendar. But next month we may discount this.
Come to me, I'll give them to you for 10.
Starts off in January. It's going to finish off in January 2017. Kind of give you the idea of how the motions on planets revolve around the planet, around the sun. One of my favorite parts coming up right about here when Earth catches up with Mars. I love Mars right now. Now, when it highlights this, when it gets here, that means it's observable from Earth. You can see it. See, Mercury comes into view right now. That's why it's highlighted like that. So what month are we on? May? June. June now. So you can kind of see it. Saturn and Jupiter is pretty slow at passing. Now, Neptune is coming into view right now. We do have a couple of asteroids here. I know faster than that. Anyways, and of course we have the phases of the moon that's happening right about here too. September right now. October, November, catching up to December. Yeah. Sorry. Right here. Okay, now, seen from Earth, this is my next picture for the planet, so you can see you're pretty much too close to the sun to be observing. We have Mars here, Venus, Saturn's right about here, Mercury, and of course we have Jupiter. So this was set around 12:30 in the afternoon. Next we'll have, do I have this yet? Yes, okay, this is what I want to talk about, the comet, 45 Honda. Apparently it's going to be visible around December the 25th. I just discovered this a week ago. Fortunately, it's going to be quite low in the sky. I don't know how it's going to really stand out, but I was told it's supposed to have like the size of 30 degrees, 30 arcs across. Is that correct? But I'll tell you a little bit more about it. What else do we have to talk about? Well, of course, Mars is still kind of out there to do something there, I guess, pretty low in the sky. So, how do we get back to? Okay, so again, this is at 10 p.m. Just to kind of give you an idea, we have a lot of Milky Ways right out here. It doesn't really stand out too much. And of course, we have the full moon. If we're doing the observing tonight, it's going to be pretty much a full moon, so that's not going to really happen. And two, because I got another commitment to do, so I'm not going to have a observing night tomorrow. I'll have another night. What else? Okay, now for the celestial calendar for this month, we have 2 meteor showers that's going on. One is, of course, a Gemini, and then one's the Earth's meteor shower, and that's about it. We have one thing I kind of pointed out, but one thing that's really kind of nice to point out is that the distance from the Earth from here and here, it pretty much it's the same almost every month. It's still going to end up around back to 406,800 kilometers almost every single time. I didn't really notice that until I started taking notes about the moon. Okay, of course, about the solstice on the 21st, and of course, the last quarter of the moon is going to happen on December 21st, which is pretty good because we have the Earth's meteor shower. Next, what do we have? Okay, well, a little bit about the Gemini meteor shower. One thing I kind of found out was kind of surprising. Most meteor showers, like what, mostly debris left from comets. Well, this one was left by an asteroid. So, and unfortunately, because it's going to peak on December the 14th, in a couple of days, we have the super moon. So, we're not going to be able to see much on that night. Of course, it's a pretty small asteroid here. Next, what do we have? Here's a meteor shower, okay. Promising, if it's clear, but I don't know how cold it's going to be. Of course, December 21st, I'll probably be still working with me, with my new job. Of course, the count should be roughly about 10 meters per hour. What else? Of course, it's when the moon, okay, so the moon might start to rise around 2 a.m., but it's supposed to, the ideal observing time would be December 21st to have a look at it. All right, what else do we have? Okay, this is the Comet 45P Honda. This is something I just discovered. This is a set and rise time, transit time for Winnipeg. I have no idea how it's going to look, but according to the simulator, it might be promising. Now, the one point I want to make is there's a few comments. I'll have more about it next time, my next meeting about it. There's a couple of comments that are actually hitting quite close to Earth. Now, this is Comet 45P. This is roughly some data that I have on it. This was discovered in 1948. The working period, of course, is 5.52 years. Okay, and it looks like it has a pretty long tail. Now, what else? Okay, now this is what I want to point out. This is, of course, this is December right now. This is where it's at in December. There's Earth. So roughly, this is the path of the comet. Now, there's Earth. They're going to come pretty close. In February the 14th, I think the simulator kind of said. So, but unfortunately, when it does hit Earth right about here, it's too low below the horizon to actually see it. But if I do make it out to Arizona, maybe we'll take some pictures. Yes, that's what I'm telling you. All right. Okay, next slide. Now, this is what I try to calculate for how close will it get to Earth. I don't have any real data for it, but looking at February the 16th, that's how close it's going to get to Earth. So there's another comet too that's going to be hitting close to Earth. I don't have much data on it. Like I said, I'll explain it next meeting. Some simulator has it, others don't. I don't know why, but it's kind of weird. And it has a very weird name. It doesn't have a real name. It's just a number. Okay, a little more about Comet 45P. Okay, I said December 25th, but I did some calculations here. this is the highest it's ever going to get. It might get a little higher, but starting in January, it's going to dip below the horizon. So hopefully we might be able to catch something before it gets too low for the horizon. Where, so I have the other comet here. Yeah, there's 2P here. That's another comet. That comet is going to come pretty close to Earth, but it's going to be between Earth and the sun, so it's going to be more of a daytime comet. So hopefully, we'll have a look at it, and I'll probably take some pictures on it. Of course, I have the phases of the moon here. You knew there. Okay, so again, this is the Earth's meteor shower here. So hopefully we have. I hope it's a good night. First, it might be a little cold. And what else? Oh, I guess that's it. That's all I have.
Well, even though it's pretty low, if the comet's got any kind of brightness, it'll certainly be observable and photographable, even positioned where it is. So now we have Ian with us for What's New?
What's in the news? I thought I would start out with something a little bit different. A newspaper. I hope everyone can read that. There's some late-breaking news here. Alexander the Great is dead. Okay, so this is about 2,400 years old. Okay? And these are little clay tablets, and fortunately some of them have actually observed for a long period of time. This is what happens when you have wars, fires, and things like this that fit into clay. And this is just a sample from the British Museum. But the scribes of the time actually recorded lots of weather, astronomical events, and occasionally what happens, as recently, is that there's useful information there, but it just often takes a while to get it out. In this particular case, we have some diaries, presumably of auroral events. And anywhere from about, I think, about the 7th century BC up to about the 2nd. Okay, so there's records on it. Of course, you all had lots of fun reading that first tablet. And that is, in fact, quite immature. So these are transcriptions. And if you've ever been in the business of translation, you know also there's a fair amount of interpretation necessary. And one of the things about certainly old records such as these is, how do you know they're talking about something of astronomical interest? Well, there's some very suggestive things found in a number of these tablets, where you refer to a very red rainbow, before sunrise, okay, and redness. All right. Now, does that strike you that it might have something to do with aurora? Probably not regularly for us, because our aurora certainly don't look a lot like this often, right? We see a different color. I mean, this is sort of possible. Now, why would these particular events be of interest? Well, the latitude of Babylon is round about 30 degrees. So if you have auroral events that far south, okay, it must mean that the sun is really active at that time. Right? And so that's of interest certainly to solar physicists. Now the other question is are you likely to see them? After all, you've probably all seen these pictures of the auroral oval, right? And it's canted on the wrong side of the Earth, right? Some murmurs of agreement around here. Well, it turns out that the auroral oval actually just wanders about the globe a little bit. You can see where Babylon is, and you can see some of the outer limits of where you might expect to see auroral activity. And so here down below, we actually have an indication of what auroral activity might be over a period of some thousand, almost 10,000 years. And basically the record is derived from other sources as well. But it's nice to have
the nice thing about written records is that they do confirm a lot of things that we are interested in. We've got nice records of eclipses, for instance. They reassure us that, you know, the solar system is a pretty stable sort of system. Probably one of those things that you hadn't thought about. So, that was my I think astronomers really love false color pictures. Okay? They're big purple thing up at the top of interest. That's been in the news lately. Of course, we all know what we're looking at. Well, what's been in the news lately, of course, is the newer Pluto, right? I mean, there's been lots of good information that's been coming our way over the past little while, and I'd like to show you just a very quick sort of movie of some of the detailed pictures that we have of Pluto over the past little while. We already have seen some of this, but it shows you that Pluto is a much more interesting object than we might have been looking for. It seems to be a little washed out. So it's a very interesting thing along there, and it's certainly going to be an area where people are going to be busy trying to figure out what's going on. But the most recent, so we have frozen nitrogen on Pluto, so it's not exactly very warm out there. Non-cellular nitrogen planes. And I think you see, we're just not getting away from the nitrogen ice at all. And I think that actually passed. I mean, this section actually didn't want to stop. So you got to see a little bit more than I expected. But not a problem. And the other thing too, of course, are the moons. And the moons are important, okay, because they do tend to, well, there's a number of things when you've got moons, because you can determine masses very nicely. There's tidal forces that come into play. Walk orbits. And the other thing too is that they can find tidal heating also into it. Of course, what's been in the news lately is the inference that there is a large underground ocean on the planet. It looks like we can build up some sort of notion. Okay, here we've got Sputnik Militia, which is the area of the ocean, the purplish bit that we saw later on. A long time ago, there was a suspicion, of course, that there was an impact from another Kuiper belt object, and we got a planet in this particular region, and we've got a change actually to the tilt of Pluto's orbit as well. Of course, this is inferred at the moment, and no measurements need to be made. You can actually sort of infer it from a number of mathematical calculations that we've got something of that sort. But what would be the nature of this ocean? Nitrogen ice, a little bit different to deal with, and probably slushy ammonia underneath. Okay, good antifreeze. It keeps things sort of. All right, on to item number 3. Nothing like a nice graphic to start us off. Okay, a dark energy spectroscopic instrument. There's been a number of improvements that have been going on. Actually, this is a project essentially to have a look at some of the early history of the universe. And what it requires is a good telescope. And so what we do is we retrofit a telescope. We've all done this sort of thing, right? So we put on a field reducer and field flattener. But the scale of this one is a little bit different. You see that black tube up there? Basically, that's what's being replaced by this yellow and blue guy up there in the corner. Some sort of sense of scale. There's a bunch of people standing around it. And what you're going to fit in there is not just one lens, but a series. And the last of that series of lenses is just shown up as a line. And you might be able to see some little faces sort of through the line there. And just give you some sort of idea of the scale of things. So you can perhaps demonstrate it. So we increase the field of view a little bit to about 3.2 degrees. And what this project is going to do is to provide a 3D map of most of the northern sky. It'll collect redshift data. And if you really want a buzzword to throw around, it's looking at baryonic acoustic oscillations. And of course, we all know what that is, right? Good, then I won't say anything more about it. Basically, if we have a look at the early history of the universe, what we have, we've all probably seen these beautiful pictures of the cosmic microwave background and the fluctuations. The fluctuations, of course, tell us something about the early history. Well, it turns out, in fact, that if we have a look at galaxies early on in the history of the universe, it will also provide us independent picture of what's going on there as well. It's basically another probe into the early history of the universe. Okay. And my last little item, okay, has to do with globular clusters. We've all taken pictures of globular clusters. And the importance for globular clusters is basically tied up with our understanding a little bit of the formation of galaxies. And here we have a picture of the Milky Way galaxy. It's taken by code in the infrared. Globular clusters, the way we see them today, are scattered in a halo around the disk of the galaxy. One of the building blocks of the galaxy. Now, one of the things that we expect in the formation, early history of the universe, that we get lots of globular clusters. And we have galaxy formation as well. And of course, we know our own Milky Way is guilty of this too, a little galactic cannibalism. Okay, so we have mergers. Okay, and a lot of the globular clusters also sort of get destroyed in the process as well. One of the interesting projects that's on the go is has this nice acronym, Apogee. It comes basically at the Apache Point Observatory Galactic Evolution Experiment. And this particular project is interesting because it focuses on the infrared. What that practically means is that you can probe through our galaxy. Basically, it sees through the dust if you choose your wavelengths appropriately. The other thing about infrared, if you choose your infrared frequency you like appropriately, you get to see the dust. Well, tune it a little bit over and begin to see through the dust. And what this project is actually doing is looking at lots and lots of stars. And one of the things that you can do is determine a little bit about the composition. Essentially, what you're doing is computing the metal to hydrogen ratio, and you can plot the distribution through the galaxy. The interesting aspect of this is that you notice, okay, that there's a difference as we look towards the center of the galaxy and then we look farther away, sort of almost immediately. And what this project has in fact done is detected stars which have a higher composition of magnitude than you would expect. If you have a look at the clusters, okay, they have higher abundances of nitrogen as well. Okay, so now we know perhaps where some of those stars from those original black hole clusters came from. So we are able then to have a look, okay, at Sidney Harris's cartoon a little bit more. Perhaps in a friendly way. We often in astronomy do a little bit of hand waving. We know we need to go from one place to another, and sometimes then a miracle happens, but we don't do quite those terms. Okay, so what we do is that go for an explanation, and go to the baby that explanation.
Particularly appropriate that we have a talk from Dr. Danielle Kahoud tonight because Danielle is new to Winnipeg and she's new to the Winnipeg astronomy community. She is not only in charge of the planetarium and the observatory, or at least charged with administering it, I guess, and she is an instructor in the University of Manitoba Faculty of Science at the moment. And still getting her feet, I would say wet, but snowy in the Winnipeg climate. She's out of the University of Alberta and Boston University, and as you can see from the title of her talk, she's fancies herself as a specialist in one component of the sun that we are all pretty familiar with, those of us who have a telescope and look at the occasional comet. So I think we'll welcome Danielle to give us a lot more knowledge about a subject that we deal with peripherally. Thank you very much.
I'm delighted to be here. I'd like to say a special thank you to some friends of mine and to some of my students. I'm really glad to have you guys in the audience. So today, I'll be telling you about the solar wind, which was the topic of my PhD. And I'll be giving you kind of a historical overview, and I'll be touching on many topics. And so we'll start with kind of the historical clues that the solar wind existed. When most of us think of the sun, we think of this perfect, featureless, glowing orb. And I don't recommend that you look directly at it, but the sun has a lot more than meets the eye. And I'm going to kind of walk you through history to tell you about the things that gave us our first clues that a lot more was happening with the sun than just this glowing orb. Then I'm going to talk to you about the solar wind, my personal favorite, and tell you kind of the typical conditions of the solar wind at Earth. I'll focus in on two special structures that tend to interact with the Earth and the Earth's environment. Co-rotating interaction regions, which were the topic of my thesis, and coronal mass ejection, which you're most likely more familiar with. I'll talk generally about the effects of space weather, and then I'll conclude with how that affects habitability on Earth and potentially on planets that we're finding around other stars. You are welcome to interrupt with questions at any point if you'd like, and I'm very happy to answer as many as you have at the end. All right, so the first clue that the sun was not a featureless orb occurred when there are four different contenders for this title, but I'm going to give credit to Galileo Galilei. In the 1600s, when he pointed a telescope at the sun, he noticed that there were these dark spots on the sun, and very creatively he called them sunspots. I thought I would be clever and post a picture of the sun today to be like, look, there are sunspots. But this is the sun today. And you can see the trailing edge of a sunspot here, but the sun is very quiet at the moment, and there aren't really any sunspots. This image is taken by the Solar Dynamics Observatory, which is a recent mission by NASA, and I'll be showing a lot of incredible images from this spacecraft. But starting in the 1600s, with Galileo, we started tracking the sunspots, and he noticed that if he observed from day to day, the sunspots would move. And this indicated that the sun actually rotates. And while he didn't know exactly what caused the sunspots, he knew that they were features that were fixed, for the most part, on the sun, and that they rotated along with it. And so he discovered that the sun rotates, on average, once about every 27 days. As he kept observing, he also noticed, and we started taking very regular observations and recording the number of sunspots starting in the mid-1800s. But he started noticing that the sunspots over the course of years would change spots, and the number of them would change. And so on the left, I have an image of a typical sun and sunspot configuration at solar maximum. You'll notice that the sunspots are large, they're grouped together, and they kind of span a whole wide range of latitudes. On the right is a picture of the sun at solar minimum. And I'll talk a little bit more about what maximum and minimum mean in just a bit. But that looks very much like the sun today, in that there aren't really any sunspots, and the sun is kind of featureless. All right, so what do I mean when I say solar minimum and solar maximum, and how do you interpret this? So here I'm showing you two ways of looking at the same information. So on the top, we'll start with the top, you have heliographic latitude, so the same way that Earth has latitude, south and north, so does the sun. And this is the year. And so they took averages over months, over whole rotations. They counted the number of sunspots and the total area and at which latitude they were at. And so what you can see is starting in 1870, we started taking really good data. You can see that there's this very periodic structure in the way that sunspots evolve. And so at solar minimum, there are very few sunspots. And what sunspots there are occur at high latitudes. And then as the solar cycle progresses, the number of sunspots and the size of the sunspots increase, and they slowly migrate towards the heliographic equator until they almost seem to meet and merge, and then they disappear and cancel each other out, and the cycle starts over again. The difference between this cycle and the next is that for the first cycle, the north magnetic pole will be at the north of this, the north geographic, heliographic pole of the sun, whereas in the next one it's the opposite, and it's the solar pole. On the bottom, it's the same year span. You have the solar cycle's numbers, the solar cycle 12, 13, all the way to 24, which is the solar cycle we are currently in. And this is just total number of sunspots. And so you can see that the number of sunspots increases, and the peaks occur right around where these features tend to converge. This diagram is called the butterfly diagram, and this is a typical representation for sunspots and solar cycle activity. So we're getting a solar maximum and a solar minimum. But even with all of this data, this doesn't really tell us that there's a solar wind. All this tells us is that there is some feature on the sun that evolves with time. So the next clue has to do with eclipses. And this is something that you're all familiar with. We had an excellent talk about this a couple of months ago. And we're lucky enough to have an eclipse passing over North America in August. But in the occurrence of an eclipse, the moon perfectly blocks out the disk of the sun. And what's left is this ephemeral, wispy light structure. And so this is a drawing, a sketch done by Edward Singleton Holden in 1892 that was published in an academic journal. And it now hangs at the High Altitude Observatory in Boulder, Colorado. And so you can see that these thin wisps, the sun's atmosphere, look like a crown, and so it was called the corona. If we look at a modern image of this, you can kind of faintly see the moon. You can see exactly how structured it is. And the structure is reminiscent of the magnetic field lines on a bar magnet, which is what I've indicated here. And so what does it take to make kind of a wispy emission that isn't bright enough for us to see when there's not an eclipse? It takes a gas that's not very dense, but it also takes a gas that's very hot. And so you can think of this kind of like a neon sign. And what would cause the structure? The structure is caused by the magnetic field. So now we can infer that the sun has an atmosphere that's very hot and that has a magnetic field. The fact that we can see the structure so clearly, even though we're looking through a gas that's fairly transparent, would also suggest that the magnetic field is kind of what dominates the dynamics there. So the magnetic field is really strong. The next clue, so we have a strong magnetic field, we have a hot atmosphere, but we don't know how far it extends. So the next clue that the solar wind existed was careful observations of comet tails. People had seen comets, but comets are infrequent, and they're not they're not bright all of the time. So this is an image of Hale-Bopp in 1997, which is not the comet that was used for this observation. But a clever astronomer noticed that the comet tail always pointed away from the sun. It didn't matter whether the comet was coming towards the sun or moving away from it after it had passed nearby. The tail was always pointing away. And so that doesn't really make sense if there were nothing that it was traveling through, right? If something is moving, you expect it. If you have let's say a windsock and you're running and there's no other wind, you expect the windsock to be directly behind you the entire time. And so that allowed him, this observation, that the comet tail was always pointing directly away from the sun, allowed him to infer that there must be something blowing off of the sun that would push the comet tail back. And using careful observations of the length of the comet tail and the precise angle of the comet tail, he was able to estimate the speed of the solar wind. He didn't know what it was made of, but he assumed it was traveling quite fast. It turns out that was an underestimate, but it was still an important step towards determining the properties of the solar wind. Now the last clue is kind of an indirect one, and this is the aurora. And these are very close to my heart. This is the reason I'm in space physics. This is what really drew me to astronomy. And they are a common observation for those of us that live far enough north. But the tie to the solar wind is a little bit more tenuous. And so we've known for a very long time, and we've used for navigation purposes, that the Earth is magnetic. And so there are a lot of ways that you could generate the aurora without necessarily invoking the solar wind, so this was kind of a fluke. But in the late 1800s, Christian Birkeland, a Norwegian scientist, was trying to understand the aurora and took a sphere, put it in a vacuum, magnetized the sphere, and then shot charged particles at it. And he noticed that the charged particles would come towards the sphere, and then trace these arches that would then kind of hover around the poles in ovals. And that's very reminiscent of the pattern of the aurora. And so he deduced that this stream of charged particles couldn't be coming from the Earth. Turns out that's not quite right. But they couldn't be coming from the Earth. They must be coming from the sun. And so putting all of these together, we have sunspots that are changing and depend on the solar cycle. We know now that sunspots are regions of very strong magnetic field that push out hot plasma, and so they just appear dark. We have eclipses that tell us that that magnetic field continues up to higher latitudes and that the plasma and the gas becomes more and more tenuous. We have comet tails that tells us that hot atmosphere extends further and further out, goes much further than what we can see in eclipse images. And the aurora would suggest that the solar wind makes all the way to Earth and perhaps beyond. But there are still some outstanding questions. So that kind of all ties together to really make a case for the solar wind. But what is it? Where is it generated? What does it start? What's the difference between the corona and the solar wind? What is it made up of exactly? What charged particles? And what are some of its typical properties? So we'll start with where does the solar wind start? The solar atmosphere is quite something. So is hot and tenuous. And when I say tenuous, I mean that it's not very dense. And so what I'm showing you here are 7 images, all taken by the Solar Dynamics Observatory at very narrow wavelength bands. And so you're looking at light from different gas from different temperatures. And so this very closely matches what's visible. And then as you step this way, you're moving to gas that's hotter and hotter, with this one being the hottest. And so you can see that, one, these are not the same. And I'll make a case for the sun's atmosphere actually gets hotter as you move outwards. And so the heating mechanisms are still not completely understood. But for each increase in temperature, you actually move up in altitude. And so this continues. And so this is the highest altitude. You can see that even the sun's magnetic structure starts to become really pronounced at higher and higher altitudes. And so the temperature at one point becomes so hot that the gas becomes ionized. I used the word plasma earlier, and I'd like to explain what that means. The sun's atmosphere is so hot that protons and electrons that used to be tied together in hydrogen atoms come apart. And so the protons and the electrons behave completely independently. And the gas is underdense enough that these things will collide sometimes, but they actually get disassociated more frequently than they can collide. And so you have this whole population of gas that is essentially independent protons and electrons, things that are positively and negatively charged. And as soon as that happens, they start interacting with magnetic fields a little bit differently. So neutral gas, like we have in our atmosphere, isn't tied to magnetic fields in any particular way. But as soon as you charge that gas, the gas starts to behave like beads on a string. So it can move in little circles around the string. So in this analogy, the string is the magnetic field line and the particles are the beads. And so the beads can go in circles around the magnetic field, and the magnetic field or the string can bend and wiggle around, and the beads will go along with it. But you can't really have beads switching from one string to another. And so that changes the dynamics a little bit. And it tells you that when you see things of the same temperature tracing out these magnetic arches, you can be fairly confident that that's a plasma of a particular temperature that's following a particular magnetic field line. So this is yet another image from SDO, and this is the highest altitude and the hottest temperature I've shown you yet. And so here the magnetic features really come out, and this is a beautiful image. So you can see these beautiful arches of magnetic field looping around If I were to superimpose a visible image, you would have sunspots right under here. You can see some of the magnetic fields. But then there's also this really dark patch. And I joke around with my students all of the time that astronomers are really uncreative when we name things. And so we've called this coronal holes because it seems to be a hole in the corona. And what this actually is an area of magnetic field that's open. So most of these field lines will rise up and then connect back to the sun. So both ends of this string are attached to the sun. In the coronal hole, only one end is attached to the sun, which means that particles can swing along the string and escape the atmosphere. And that is where the solar wind is born. So if I go back to this gorgeous eclipse photo, this is also the corona, but now we're looking at all wavelengths, so we can see things that are even fainter. There's this definite distinction between magnetic field lines that seem to close in on each other and kind of form these pointed belt loops. These are called helmet streamers or streamers. And then you can also see some magnetic field lines that really do appear just to be open and to be straight. And so this is a very simplified sketch of the corresponding magnetic field with the polarities introduced. And so magnetic field that's pointed out is going to be called north. Magnetic field that's pointed into the sun is the south polarity. So you have some field lines that will rise up out of the sun and reconnect back to the surface, and then others that are open. And then these helmet streamers are where the pressure from the hot gas is enough to pull out and stretch out the magnetic field lines. So typically, we think of the fast solar wind from coming out of the open field lines, and the slow solar wind to come out of kind of the boundary between where the field lines are open and closed. And one of the reasons the fast wind comes out, from the open field lines is that the opening is narrower. And so if you think of a garden hose and you want the water to go further or faster, you cover half of the hole with your thumb, right? You close the opening, and that shoots water out. And so in this case, it's the magnetic field that's doing that to the solar wind. And so that was our sketch, and this has been confirmed observationally. So the Ulysses spacecraft was launched in 1995, and it's the first and only, so far, spacecraft that we have that orbits in a plane perpendicular to the plane in which all of the planets orbit. And so this spacecraft flew out to Jupiter, used Jupiter to do a gravity assist, and then headed south, and then swoops from south to north over the sun. And so at its furthest, it's about Jupiter distance 5 astronomical units away. An astronomical unit is the average distance between the Earth and the Sun. And so it swoops 5 astronomical units away, and then comes actually fairly close to the Sun, about 1.5 astronomical units when it's closest to the Sun, and swoops up quickly and then traces that. So on its first orbit, it measured the polarity and the speed of the solar wind. And so David McComas has become famous for making these plots. And so what we have here is a beautiful image of the sun with the helmet streamers and the corona. And then overlaid on top of that is a polar plot of the solar wind velocity. And so the way to read this is the distance from the center of this line to any point is the speed of the solar wind. So you can see that at high latitudes, the speed is roughly constant, fairly uniform, at about 800 kilometers a second. This is about 2 million kilometers an hour. So it's moving. Whereas at low latitudes, kind of overlapping with the streamer belt, you have the slow solar wind, which moves at 200 kilometers per second. So it's still very fast, but it's relatively slow. And then as you swoop south, you get the same speed profile, but these speeds are color-coded such that the red is outward magnetic field, and the blue is inward magnetic field. And so these are separated by, they're called sector structures, and they're separated by the heliospheric current sheet. All right, so that was the view from the side. Let's now consider the sun from the top down. So I mentioned when we were talking about sunspots that the sun rotates. So the solar wind is constantly streaming out in a straight line in all directions from the sun, top, bottom, side to side, all of it, but it's rotating. So now I'm going to have you guys imagine your garden sprinkler that rotates. Even though the water is getting shot out in a straight line, as the sprinkler rotates, it traces out these spiral patterns. And the solar wind is no different, with the exception that it's spraying at different speeds and in all directions all of the time. But so we're looking from the top down, the sun rotates this way. This dotted line is the orbit of the Earth at 1 astronomical unit. And so we have all of the solar wind flowing straight out, and these lines in red and blue are the magnetic field. And so at this point, the solar wind is flowing out, and it accelerates from the surface of the sun to about here until it hits a point at which it starts moving faster than the speed of sound, and the equivalent speed of sound in a magnetic field line. And that's called the Alfvén speed. And so all of a sudden you have this substance that's moving faster than any information about itself can travel. And so it's moving supersonically or supercritically, which leads to some really interesting dynamics, which I'll talk about in a little bit. But as soon as it hits that point, the flow is really what dominates, and the magnetic field lines, the strings, kind of get dragged along for the ride at this point. So you kind of have this transition of power between the magnetic field and the flow somewhere around here. But this spiral pattern of the magnetic field lines is called the Parker spiral. In the 1950s, there was a man named Eugene Parker, and he made about 18 estimates of what the solar wind would be like, and we just keep proving him right. So at this point, he has a lot of things named after him, but he made some excellent contributions to the field. All right, so another level of complexity is that the rotation axis and the magnetic axis in the sun most often are not completely aligned. And so if you think of my body as being the rotation axis and the magnetic axis being offset a little bit, the magnetic equator, and this is similar to the rotation of the Earth and its orbital plane, but if you think of my arms as being the magnetic equator, as I rotate, you flap above and below the magnetic equator. And so from the perspective of Earth, and as this flows out and spins, it creates this ballerina skirt-esque shape. And so this purple surface is a depiction of the heliospheric current sheet, which separates inward magnetic field and outward magnetic field. And so Earth's orbit, which is drawn tiny here, transects these regions it transects the heliospheric current sheet and will alternate measuring inwards and outwards magnetic field. All right, so that was the magnetic field. What does that look like for speed? What I'm showing here is one of my heliospheric simulations. So I do computer modeling. And so I'm showing you a latitude versus distance. You can think of this as if I had a whole sphere. It's Christmas, does everybody know those orange chocolate eggs, the candy eggs? You smash them and then the pieces come out. I'm showing you chocolate orange slices of the solar wind. And this black line is the plane where the Earth orbits. So the Earth orbits about exactly halfway here. But the solar wind along this line is what's going to sweep over the Earth. And so you can see, just like you saw in the Ulysses plot, that there's, so this is solar wind speed, this is fast solar wind in red, and slow solar wind in blue indigo. So for 6 different slices in longitude, you can see that There's always high-speed solar wind at high latitudes, and lower latitudes are kind of a mix between fast and slow. And so there's a lot of variability in what the Earth sees. So if there's a lot of variability, what are some of the typical conditions? So the average solar wind speed that the Earth sees is 400 kilometers a second. The average density is 5 particles per cubic centimeter, which is ridiculously low. I did a calculation today, and I was like, okay, if I were to take 1 centimeter cubed of air at standard temperature and pressure, what volume of solar wind would I need to have the same number of particles? And the answer is a 10 kilometer by 10 kilometer by 50 kilometer cube of solar wind to fit into a tiny cube of normal Earth air. And so when I say tenuous, I mean tenuous. All right. So what is the typical magnetic field strength of the solar wind? This is 5 nanotesla, and this is about 1,000,000 times weaker than your typical fridge magnet. Okay, so we're not talking very strong magnetic fields and very strong densities, but they still have a noticeable impact on our day-to-day lives, which we'll talk about later. So those are the average numbers, but the range in speeds is between 200 and 800 kilometers a second. The range in densities is between 1 and 30, and something like 30 is going to be due to one of the special structures that I'll talk about later. And the magnetic field also varies between about 1 and 20 in magnitude. That will vary also in terms of direction. All right, so no more teasers. This is one of the special structures. So we talked about variability, we talked about the rotating solar wind. So the structure that is near and dear to my heart are co-rotating interaction regions. And these occur when you have a source of fast solar wind that's aligned next to a source of slow solar wind. As the sun rotates, the slow solar wind will take off. And then a little time later, the sun rotates the source of fast solar wind in behind it. And then the fast solar wind gets launched. And so this acts just like a snowplow, which I'm sure many of you have seen on the roads recently, right? So it catches up to, and because you have this magnetic field, and we're still working with the strings and beads analogy, you can't just have fast solar wind pass through slow solar wind the same way that a gust of wind on Earth would. Instead, you get this tangled mess of beads and string snowplowed forward, and you get this spiral-shaped pressure ridge, and the ridge is bound on the forward side, so the side that the solar wind is propagating on, and on the reverse side, so trailing behind it, by these pressure waves. But it's this big spiral-shaped structure. And this is an attempt at kind of depicting this in 3 dimensions. And so oftentimes, as you've seen, the source of fast solar wind isn't this homogeneous line. It has some shape to it. And so these will often be inclined. And so as the fast solar wind pushes forwards, it will accelerate and deflect slow solar wind away from it. And this is just like when you push your shovel, you always get the 2 trails behind you of snow as snow deflects around the shovel. And you have fast solar wind coming up behind this and also getting deflected. All right, so this is another one of my models. And so this is looking down on the equatorial plane of the sun. And so this is a solar wind speed as a function of azimuthal angle. So we're looking down, looking at the whole 360. These black lines are actually where I took those orange slices earlier. So again, we have solar wind speed. And what you're seeing is a number of stream interaction regions developing. And this pair are the 2 that I was showing you earlier. But you can see that they seem to have different amounts of winding. They have different kind of azimuthal widths. They have different maximum speeds. And so there are a lot of things that will really affect how these things evolve. But there are typically 2 or 3 co-rotating interaction regions per solar rotation, and they're always present in the solar wind. So no matter the phase of the solar cycle, these things are recurring features that occur roughly every month. But the co-rotating interaction regions will also evolve as they travel away from the sun, and so usually by the time they sweep over Earth, they're still growing. They're kind of in their teenage phase. They hit maturity at about Mars, and that's when they're strongest and angriest. And then after that, they actually start to dissipate a little bit. And so by the time they hit Jupiter, they're not quite as powerful. But what I study is how things like the steepness of the speed transition, the three-dimensional shape, the change in density, what comes before it affects how these things evolve. And I look particularly to see whether or not this forward and reverse pressure wave that I was talking about develops into a shock. And so a shock occurs when something is moving faster than the speed at which the information can travel. So a good example, it isn't quite day to day, but the Concorde jets that travel faster than the speed of sound. They fly over you, you see them, and then a couple seconds later you hear this big boom, right? And so I'm looking to see whether or not these things will have a boom. And so why does that matter? The analogy I'll give you to kind of motivate this is if you're sitting in your parked car and you have somebody drive up to you, stop, line their bumper up next to yours, and then start accelerating, you have time to react and get out of the way. And it won't really damage your car, I guess maybe depending on the quality of your bumper. Whereas if you're parked in your car and somebody comes at you and they're already traveling at 80 kilometers an hour, even though, because that speed transition is happening so quickly, it's going to have a completely different effect on your car. And so, if you think of the Earth's protective bubble, the magnetosphere of that car, if something changes kind of gradually, it has time to adapt. Whereas if something changes really quickly and a shock passes over it, you'll have a much stronger reaction from the Earth's magnetosphere. All right, so what I'm showing here are those same orange slices. So this is the same velocity plot you saw earlier. And this here is density scaled with distance. And so purple is low density, and green and red is high density. And so I'm looking at two different co-rotating interaction regions. And so you can see one here that comes from this little bubble of medium speed wind. It has a really interesting structure as it evolves. There's another one right here that actually gets to a really high density, much higher than this one. And so why is it that one of them gets to a much higher density than the other? Why is it that they have different widths? What are the parameters that control those? All right, so I mentioned a little bit already that these don't really, CIRs don't really change with solar cycle. But the rest of the solar wind does. So we'll talk a little bit about how that happens. So during solar maximum, the orderly structure of the solar wind completely disappears. And so this is the same image that you saw of the solar wind from Ulysses at solar minimum. And this is the equivalent rotation of Ulysses, orbit of Ulysses, at solar maximum. And so you can see that there's fast wind and slow wind at all latitudes, all over the place. There is no rhyme or reason to the magnetic field structure. The magnetic field's pointing inwards and outwards. The corona and the streamers are all over the place. And so during solar maximum, the corona is reconfiguring itself rapidly. The magnetic configurations are complex, especially low down. And any sort of sensible order disappears. But during this time is when the second special structure in the solar wind appears. And this is probably the one that you guys have heard. These are coronal mass ejections. And so these are three images of the same coronal mass ejection at different distances. So in all of these images, well, you can see the surface of the sun here. But these white circles are the surface of the sun. So you can tell that it's getting bigger looking from further away. This is the Solar Dynamics Observatory, and these two are images from Stereo, which is another spacecraft. This one's, sorry, SOHO, that's the Solar and Heliospheric Observer. And stereo is a pair of spacecraft that both look at the sun, so you get a 3D view of it. But you can see that there's this complex plasma arcade that arches over, and so magnetic field lines are kind of elastic, and so they don't really like to be twisted. So you couple that with a hot gas that wants to expand, and you'll often get eruptive behavior. And so this is what occurs here. You have an eruption, and this bubble of hot plasma and strong magnetic field erupts. And so this is the remnant of the arcade, and these things flow out away from the sun at very high speeds. And so a fast CME will be, this is a typo, so a slow CME will be about 600 kilometers a second, and the fastest will travel at 2,000 kilometers per second. So there should be an extra zero there. So more than about 3 times the fastest solar wind, which is exceptional. So it usually takes the solar wind about 3 or 4 days to get from the sun to the Earth. So one of these, the fastest, will take less than a day, which really doesn't give us much time to do anything about it, which is why we're trying to be able to predict them. They will also act as snow plows and drive compressions of the plasma. And so the densities ahead of them will be larger than 20 particles per centimeter cubed. They'll have really strong magnetic fields, larger than 20 nanotesla. But what's really important about coronal mass ejections is that the orientation of the magnetic field tends to be kind of a wild card. Most of the solar wind in the Earth's orbital plane, the magnetic field is roughly horizontal, but for these, a lot of the times you start getting a vertical component, and that interacts with and plays real nice with the Earth's magnetic field. And so these very often drive shocks, which is that car analogy. All right, so both of these are completely able to drive space weather. And so I use space weather as kind of a blanket term to describe the interaction between the solar wind and the Earth's own magnetic protection bubble. So the magnetosphere. And so what's drawn here is completely not to scale. But we have the sun, a CME, the Earth's own kind of dipole-like / windsock magnetosphere, and the surface that separates the two is called the magnetopause. So let's talk a little bit about how both of these structures affect the magnetosphere and what's different about them. And so, as I mentioned earlier, because the orientation of the magnetic fields in these CMEs tend to have a vertical component, they can sometimes be perfectly anti-aligned with the Earth's own magnetic field, which on the nose, on the direction that faces the sun, which for some reason, space physicists, the sun is always on the left, always. But what will happen is, if you get a magnetic field that is getting squeezed together of opposite orientations, every once in a while it'll say, I've had enough of this, and it will reconnect. And so what I mean by that is it will decide to connect with the part that's oppositely oriented, and then because the rest of the magnetic field on it is still attached to the solar wind, is getting peeled back, you get this cycle called the Dungy cycle, in which you have an opening of the magnetic field lines on the nose. It's not all the way, just part of the way. So we're kind of peeling back layers of an onion, but there's magnetosphere. But this field line that's still attached to the solar wind gets peeled back, and that will drag back the magnetic field lines here. So here the Earth's magnetic field is in red and the solar wind is in white. And so you kind of get this reorganization, this reconfiguration of magnetic field lines in the Earth's magnetosphere, which will cause aurora, it will accelerate particles, and it will also inject particles from the solar wind into the Earth's magnetosphere. Our magnetosphere is mostly filled with particles from our own atmosphere. Conversely, co-rotating interaction mediums often don't have that vertical component of the magnetic field. So what they do instead is they just kind of compress and squeeze the entire magnetosphere. But they tend to last longer than the CMEs, and they tend to recur more frequently than the CMEs. And so you kind of get this regular squeezing and relaxing of the magnetosphere, and that's very efficient at generating waves. So the analogy to strings and elastics holds in the magnetosphere also. And so, you know, if you pluck a guitar string regularly, you're going to get beats and amplifications. And the same thing holds true here. And so if you get these regular wave generation events, you'll accelerate particles, particularly in the radiation belts, which are two regions that are depicted in kind of bluish here, which conveniently is where a lot of our spacecraft like to reside, or need to reside. Which leads me to the effects on our day-to-day lives of space weather. So this is a complicated, busy diagram, which I did on purpose, because there are a multitude of ways that the solar wind can and does affect our daily lives. So in both of the CME and CIR-driven storms, you'll get similar effects, but to different degrees. And so you get galactic cosmic rays that will come in, and those typically come from supernovae. But you can get particles from the sun that have almost the same energy. And so these will affect the ozone. They will charge some of our spacecraft. They will damage satellites. They will pose radiation hazards for our astronauts. As transpolar flights are becoming more and more common, those are more and more susceptible to radiation damage. It also interferes with radio communications and radar accuracy. The particles raining down will increase the amount of electrons in our upper atmosphere, which is harmful. It's not harmful for us, but it does affect our GPS accuracy by quite a lot. A really extreme event, you can actually induce currents in the atmosphere, which will induce kind of mirror currents on Earth. And so you can blow up power grids, you can blow up power transformers. So in the late 80s, most of Quebec lost power because of something that happened on the sun. And so we're talking about magnetic fields that are 1 million times weaker than your fridge magnet, blowing out power grids, which is mind-blowing. And so as oil pipelines become more and or less of a thing, these will become corroded because of these currents. And so there are a large number of ways in which our day-to-day lives become affected by space weather. And as a society, we're becoming more and more reliant on our space-based assets, on communications, on GPS, on our phones. Yeah?
There was that huge event, what was it, in the 1860s, where they
Yeah.
were electrocuted.
Yeah, so the Carrington event is named after Richard Carrington, and it was September 1st, 1859. And that was, not that I've studied this one a little bit, but that was a once-in-a-century type CME. And so it was one of the most energetic. And they've done simulations to try and recreate it, because we didn't have any instruments out in space at the time. And so they estimate that the CME that was launched must have been traveling at about 2,200, 2,400 kilometers per second, and had a magnetic field oriented like kind of right in the sweet spot. And that storm was so powerful that you could see aurora during the day. It was lighting telegraph poles on fire. They were sparking. They unplugged the batteries and kept sending telegraphs. You can actually read the transcripts. They're hilarious. And you could see the aurora all the way down to Mexico. It was unreal. And so we actually suspect that, we're due for one of these, and we think that the sun may have launched one. It was either last summer or the summer before, but it was aimed in the opposite direction from here. But if something like that hit us today, it would be disastrous. It costs a lot of money and it has cost a lot of money to build our space-based infrastructure, all of our weather satellites. And so if we don't power those down or take the necessary precautions, we can be looking at watts of damage. So we haven't had one quite like that hit us since. But it's important to know whether or not it's coming in, so that we can do something about it. All right, so despite this kind of extreme example of all of these ways that it affects our lives, the sun's activity, magnetic activity, still has allowed life on Earth to develop. It hasn't necessarily been hampered. And that's partially because of the Earth's magnetic field. But still, that interaction is an important one. And so these are today's statistics for the Kepler spacecraft, which is looking at a small patch of sky and counting how many exoplanets it can find. So exoplanets meaning planets around other stars. And so far, there are 2,331 confirmed planets around other stars. There are 4,696 candidates, so those are maybes. We need them to do a couple more rotations so we can confirm them. Out of all of those, there are only 21 in the habitable zone. And what I mean by habitable is that the planets are about the right distance from their star for liquid water to exist. If it's too close, it's too hot and everything evaporates. And if it's too far, it's too cold and everything is frozen. You also need the planet to be rocky. If it's a gas giant very close to its star, it makes things a lot more complicated. But still, so this image is a distribution of the size. This is an artist's conception. We don't actually have pictures of these. But this is a representation of the size of all of the exoplanets that have been found so far. So a lot of really big ones, a lot of really small ones. And this, I think, we're really good. Our current techniques allow us to find very big planets that are very close to their stars. And so this distribution might change as our technology gets better, as our analysis gets better. But even for those 21 planets in the habitable zone, you need to consider the star's activity. A lot of these planets have been found around stars that are smaller, cooler, but more magnetically active than our sun. And the closer you get to the sun, the stronger its magnetic activity affects you. And so these 21 haven't really been studied in terms of space weather or stellar weather. And so even if you had a planet in the habitable zone, if it, for some reason, didn't have a protective magnetic field, it would be getting inundated by charged particles and radiation all of the time. And so it's one more factor that needs to be considered when we're looking for life in other planets. And it's one more reason that the Earth is kind of at the sweet spot of our solar system. Venus and Mars are close to the habitable zone, but neither of them have this protective magnetic field. And that concludes my overview of this one. Any questions?
Excuse me, what is the source of the magnetic field of the sun? And is it similar to the source of the magnetic field of the Earth?
Okay, so I'll come back to you. Sorry. So there was one question. The first question is, what is the source of the magnetic field on the sun? And is it similar to the source of the magnetic field on the Earth? I can't really talk to the source of the magnetic field on the Earth, but I can tell you how it's generated in the sun. So the sun has a core that is dominated by radiation pressure, and so that rotates like a solid. But it does have a small magnetic field running through it. Actually, I was really clever. Okay. So I anticipated some questions. So
We don't know each other, right?
No. So the core rotates like a solid, but the outer third of the sun is getting heated from the bottom. And just like a a pot of water gets heated from the bottom, starts to convect, that layer of the sun convects. But it's also rotating, so you get this rotating convection. And as soon as you get a little bit of a magnetic field, it gets wound up and spun up and strengthened. It's called a dynamo. And so the magnetic field gets built up that way. Does that answer your question? Yeah. Sorry, there's a question here.
I was wondering about white dwarfs. Our sun is eventually going to be a white dwarf, and which will be convenient at the time, because it will be mineable for diamond.
If we're still around to mine it.
And so I was wondering, are there any other such resources available now, or are they within proximity, or do we have to wait for this and have a pleasant impact for the dispersal of such rocks or stars from countries and stars?
Okay, so to make sure that I understand your question, is there a source other than our sun dying that's nearby for us to mine?
Well, I'm just using our sun as an example. So it's out there, whether it's in solitary formation or in isolation, it's part of the binary star formation. That is that there are white dwarfs out there, and there are carbon stars that are made entirely of diamonds that are which is very precious. So there are purposes for composition and what have you. Certainly use them. So just saying in addition to exactly such as exoplanets, extraterrestrial stars, older ones. If there's something we can mine, there's something we can use, and we can visualize
I'm not sure where the question was.
All right. Okay, so to paraphrase, if I understand correctly, is there a way for us to mine resources that do occur naturally in the dying processes of stars? While I'm not an expert on this, everything is so far away. Like any other star is so far away that right now we don't have the technology to get there in a time frame that's feasible for practice. It would take us multiple years just to get to Mars, and even the nearest star is orders of magnitude further away than that.
Cheaper to make artificial diamonds.
Should we send a probe to approximate some very meteors if the magnetic field is strong?
Oh, you're asking me about the magnetic field of a different star? I like ours. I believe so. Full disclosure, it's true in the exoplanets. It does have an estimate.
So, that's the
Oh, okay. So if you're blurry, probably not. I probably don't answer. I see it. Right. Yeah.
For co-rotating interaction regions, have you discovered any evidence for the shocks that you're talking about?
Yeah. So, so Regan's question is, have we discovered any evidence for the shocks? So, in the past couple of decades, we've actually been able to put a couple solar wind probes that sit out in the solar wind all of the time. One of them is called ACE, and another one is called Creatively Wind. And both of those have very high time resolution, and they'll just measure particle speed and particle density. And we've seen changes, really rapid changes, in the solar wind properties for both CMEs and CIRs right in front of the Earth. So not only do we know that they shock, we know that they will shock within Earth's orbit, but not all of the time.
Rapid, like microseconds?
Yeah, okay, so that's a really good question. So the fastest time resolution we have on ACE and wind I think is 2-second resolution, which may not seem that fast. The formal, there are 3 definitions to shock. The first one is a theoretical definition, which is infinitely thin and difficult / impossible to achieve in real life. When we're talking about a magnetized fluid, which is the solar wind and the plasma, these particles, these beads on a string that I was talking about, they'll all orbit, and depending on their energy, they orbit with a particular radius. And so if you get a rapid change in the properties on a size scale that's smaller than that radius, we call that a shock, because the particle really doesn't have time to adjust before its own orbit takes it into something completely different. And we've observed that. And so that's kind of the working definition.
One more question.
Right.
Sure, I mean, this is not my field at all, but I find it really interesting. And I'm just wondering about the knowledge transmission. So you talked about how this research can help telecom, prevent certain events that would be catastrophic, right, for our ambulance. So how is this knowledge transmission received by, say, telecom or,
Right.
Yeah.
Yeah, that's a good question. So I did my PhD in the States, and I started to talk to more about the situation there, but I am assuming that it's similar to Canada. The NOAA, the National Ocean and Atmospheric Administration, the weather people have a subdivision dedicated to space weather. So there's an organization called the Space Weather Prediction Center that will make forecasts similar to terrestrial Earth forecasts. And things like telecommunications and power grids and airlines actually receive daily forecasts and updates. And so there's a website, and so there's a whole dissemination you can subscribe. So there is a information dissemination. And the people that are at the highest levels will actually come to scientific conferences, and there's some interrelationship between the research and the operations.
If you go to spaceweather.com, you'll find a lot of things that lead into the area. Well, thank you all very much. And thank you. Canvass the group afterwards to find out if you still want to keep on going to the hub or whether you want to switch back to Boston Pizza for the next meeting. The hub has certain attractions like cheaper prices. So anyway, I've ordered quite a few pizzas.